Hello again and welcome to another video lesson with Lawson. Today we're going to continue our description of kinematics, really looking closer at velocity and how it relates to descriptions of motion. When you think about velocity, there's a couple of things that should automatically come to mind. The displacement is the integral of velocity with respect to time. Works out that the integral is the antiderivative, so it makes sense if the derivative is one direction, the antiderivative would take you in the opposite. Acceleration is the derivative of your velocity with respect to time. It turns out that they create a nice little daisy chain between your derivative of displacement with respect to time is your velocity, the derivative of your velocity with respect to time is your acceleration. That means the integral of your acceleration with respect to time is your velocity. The integral of velocity with respect to time is your displacement or change in position. Those statements are going to become very important as you're working through different problems in terms of trying to determine either the displacement, the acceleration, or the velocity based on a given function. We're also going to look closely at velocity graphs as the next step after we've already spent some time looking at position graphs. Key features of a position graph tell you information about the motion that may look similar but are very different than the same features on a velocity graph. And as you can imagine, when we look at acceleration graphs, we'll notice again those key features from one will look the same on the other but actually have a different meaning or give you different physical information about what the object is doing while that motion is taking place. Or in the rare instance, where we actually have a graph that shows no motion is taking place. Some of the important features to be aware of on all of these graphs, but we're going to first look at here for the velocity graph, is a horizontal line. A horizontal line on a position graph means that you are remaining at rest and you're not moving, regardless of where that horizontal line is. On a velocity time graph, it actually changes. A horizontal line only represents a lack of motion or no change in position when it's along the x-axis, when the velocity is 0 for that time period, because in order to not be moving you must have a 0 velocity. If you have a horizontal line anywhere other than along that x-axis, then you're in motion, and if it's above it you're moving in the positive direction, if it's below it you're moving in the negative direction. So it's one of the key features to be aware of and be able to look at when you look at a velocity time graph. Another feature of velocity time graph is whether or not you see a linear or curved shape in it. A linear velocity time graph, in one case horizontally, means it's constant, or at an angle means it has a constant slope. That represents a constant acceleration. So when we have a velocity graph that's linear, either the acceleration is 0 or the acceleration is a constant value along that line, which we can find by finding the derivative or what is the slope of that line. When we end up having a curvy velocity graph, something where it's not linear, not only does it have a changing velocity, it has a changing slope, which means it has a changing acceleration. So when we have a non-constant acceleration, the way we'll see that in a velocity time graph is by seeing a curviness to that graph. This velocity time graph shows that as time goes on, the velocity is 0. It's along that x-axis. The function of velocity in terms of time is 0. Showing that no matter what time input you get, the output is 0 meters per second. There's a couple of interesting things we can do from that. One is we could look at what the acceleration is. Since the acceleration is going to be the derivative of the velocity with respect to time, and we know that that velocity is 0, the derivative of 0 is 0. It confirms what we already knew. There was a non-changing velocity, and when you don't have a change in velocity, you can't have an acceleration. The acceleration is required to be 0. We're looking at the integral from our initial time to the final time of our velocity with respect to time in terms of time. What we find is that the integral of 0 is a constant c. So we'd have c at t, we'd subtract from that c at t naught, or a constant minus itself is always 0. So we find that your change in position or displacement of this velocity is 0. While we know that our change of position is 0, it doesn't actually give us any information about what our initial position or our final position was. In order to be able to determine the initial position or the final position, or just the position since it's not changing, we need some additional information about either the coordinate system or where the object is located relative to some arbitrary origin or some other arbitrary landmark. Once again, we see a horizontal velocity. In this case, it's above the x-axis. It's no longer along the x-axis. In this case, the area between the line and the x-axis is not going to be 0. So we know that the area under the curve, otherwise known as the integral of this function, is going to be our displacement. We know that we're changing position. We also notice something interesting about how we're changing position. Since we're moving at a constant velocity, by definition, we're changing the position by an equal amount every given second or every given time interval, as long as that time's kept equal. The change of position between the 5th and 6th second is the same as the change of position between any other consecutive seconds along the motion. Velocity as a function of time is equal to 25. Again, we can repeat some of those same steps that we just did, but using this function. If we're looking for the acceleration is going to be the derivative of our velocity function with respect to time. The derivative of a constant, like 25, is 0. So the derivative of 0 and the derivative of a constant is the same. However, when we start looking at the displacement, which is the integral of our velocity as a function of time in terms of time, we notice in this case it's the integral of 25, which is not the same as the integral of 0. The derivative of a constant is 0. We need something that the derivative will give us back 25 between our initial time and some later time t, and the integral of a constant that's not 0 is that constant times a variable. So this would be 25 times t plus c, but in this case, since we're doing a definite integral, this would be 25 times the upper boundary t minus 25 times the lower boundary t naught, or we could write this as 25 times the change in time to be able to get our displacement. The relationship, exactly how far are we moving each second that goes by. Vertical line, and then take a consecutive second or 2 seconds and create a vertical line to represent that boundary and find the area of that rectangle shown. That area of a rectangle is 25 if it was 1 second, and 50 if it was 2 seconds, and 75 if it was 3 seconds, and so on. So we can see very clearly in this example how the area under the curve, or the integral of your velocity time graph, corresponds to your change in position. What it doesn't tell us, again, is what our initial or final position is. We know how much we would change position, but in order to know the initial position or the final position, we need some other information about where the object was located. One final note, the interesting thing, again, is that the horizontal line everywhere on a position time graph means the same thing. The horizontal line on a velocity time graph means the same thing as long as it's not along the x-axis. When it's along the x-axis, it actually means something different. It means that you're at rest or you're not moving. Now we have a changing velocity. We have a velocity that's not constant at 0 or not constant at some positive value. We have velocity that starts very close to 0 and then increases at a constant rate. We know that because it's linear. If it was not changing at a constant rate, if we had a non-constant acceleration, we wouldn't see a linear shape, or we wouldn't have a line to the graph. From the function above, we see that the velocity as a function of time is described by the function 6t plus 4. If we go through those two processes again, where we know that the acceleration is the derivative of the velocity function with respect to time, we can see that that's the derivative of 6t plus 4, which ends up giving us 6 times 1 plus 0. From this, we can see that the acceleration of the object is 6, and whatever the units are corresponding to the graph. In this case, when we look at the axes, we see that the graph has meters per second for the y-axis and seconds for the x-axis, which means the slope would be meters per second, or meters per second squared, one of our standard notations for the acceleration of an object. The displacement, which is the integral between our initial time and some time later of our velocity time function with respect to time. The integral of 6t is a constant, so we have 6. T, which you can either do the variable and memorize it or the power rule, they're both the same thing. So I need the derivative to be t, so it's t squared divided by 2 plus 4, which means it's a constant, or 4 times t. Again, we can put in the values, so this would be plus c, so if we do t final and then subtract from that 6 times t naught squared divided by 2 plus 4 t naught, we see here the definite integral. We can do a little bit of cleaning up with this, because it will work out that 6t squared divided by 2 is actually 3t squared, and then we could have plus 4t minus 6t squared over 2 minus 4t by distributing this negative sign here, which is actually going to be plus 4t minus 4t naught, 4 times the change in velocity, and of course here again 6 divided by 2 is 3, that's minus 3t naught squared, 4 times t minus t naught, which is our change in time. Plug in any given time value in terms of our initial and final time to figure out what our change in position or our displacement was. Something you also notice is that if your change in time is 0, if the initial time and the final time is 0, then we'll find out that your displacement is also 0, which would make sense. You might be moving, but at any instant in time you have a constant position and a constant velocity at that instant in time. You need time to go by in order for that motion to take place. Even if it's a very, very small motion taking place, you need a very, very small amount of time to pass. Looking at this velocity time graph, while we start at close to 0, as time goes on for that initial or first few seconds, we're actually going faster and faster in the negative direction. We're speeding up as we move in the negative direction until we reach a maximum negative velocity somewhere around 2 seconds-ish, and then we start slowing down in the negative direction, still moving in the negative direction, but getting closer to 0. And eventually we reach a point where we come to rest somewhere around 4 point something seconds, and we reverse direction. So we speed up in the negative direction, slow down in the negative direction, stop, turn around, and start speeding up in the positive direction. Since I was speeding up in the negative direction and then slowing down in the negative direction, by definition my acceleration could not have been constant. In one case I had an acceleration in the direction of motion that was causing me to speed up. In another case I had the acceleration in the direction opposite of motion, which was causing me to slow down. By looking at this function and looking at its derivative, which describes the acceleration, we can probably identify where some of those time periods are, or where some of those significant changes take place. Another interesting feature of this graph is thinking about how it shows us the displacement. The displacement is the area between the graph and the x-axis. And we notice for those first couple of seconds, since we're moving in the negative direction, the area between the graph and the x-axis will actually be below the x-axis, or a negative area, which means we have a negative displacement, which makes sense. We're moving in the negative direction, so we should have a negative displacement. And then we cross that x-axis and we start moving in the positive direction, which means we have a positive displacement. There is some point, some time, where the positive displacement will equal the negative displacement, and we will pass back by the origin and then continue on moving further and further in the positive direction. We can see visually, just comparing, it wouldn't take more than a few seconds before the area created between the curve when it's above the x-axis becomes equal to or greater than the area that was bound between the curve and the x-axis for the first couple of seconds. When we're trying to describe or determine, when we're looking at the acceleration as a function of time, that's the derivative of the velocity with respect to time. The derivative of this function is 3, a constant, times t squared, which is the power rule. 3 times 2 is 6, times t to 1 less power, so it's 6t, minus the constant 12 times 1 times t to the 0 power, or 12 minus 0. So we see the acceleration as a function of time is 6t minus 12. Interestingly, some things become very obvious. When t is 0, for that initial instant in time, our acceleration was negative 12. But as t goes on, as t goes to 1 second and 2 seconds and so on, what we're doing is multiplying that value by a constant positive, and so we're getting closer and closer to a positive value. We're getting less and less negative until 2 seconds. At 2 seconds, our acceleration would be 0. At 2 seconds is when it looks like the tangent line would be a horizontal line, which indeed it is when we look at this function. And since the tangent line is 0, our acceleration is 0. The slope of the line at that point is 0. Then, as t goes beyond that, we get a number larger than 12. So when we subtract 12 from it, we'll have a positive acceleration. And as time goes on, we'll get a larger and larger magnitude or positive acceleration. Also matches our graph, where we see that the tangent to this curve would be getting more and more positive, or the slopes of those tangents would have a greater and greater positive value. Describe the displacement. That's going to be the integral of the velocity function with respect to time between our initial time and some point later. The integral is a constant and a power, 3t cubed divided by 3. And what you can see there is 3t cubed divided by 3, the derivative of that would be 9t squared divided by 3, or 3t squared, which matches up, minus the constant 12 times t squared divided by 2, minus constant 1, which is t. Would be 1 times t, right? T to the first power divided by 1. Or the derivative of t is 1. The derivative of a variable is 1. And then we'd have to subtract from that. If we were just doing the integral, we'd do that plus the constant c. But since we're doing the definite integral, we subtract from that 3t naught cubed divided by 3 minus 12t naught squared divided by 2 minus t. When we distribute that negative, a couple of interesting things happen in terms of, oh, this is t naught. So we end up with 3 divided by 3 is just 1. So we have t cubed minus 12 divided by 2 is 6t squared minus t naught cubed plus 6t naught squared plus t naught. And now we have the displacement